Welcome to Tetryonics. In this lecture we'll be covering the charged quantum geometry of radioactive elements, isotopes, and finishing up with nuclear fission processes. This lecture forms part of the series based on Tetryonic Book 3, Quantum Chemistry, with a small portion taken from Book 2, Electrodynamics, both of which are available on YouTube and Google+. Following on previous lectures from Tetryonic geometry, specifically those relating to equilateral energies and mass energy configurations and geometries, we will show in this case that the energies of nuclear fission and radioactive decays are the result of the mass energies of the charged geometry of all matter. And we will also show how the difference between mass energy and three-dimensional matter brings about nuclear decay and eventually nuclear fission. Obviously, as highlighted in Tetryonics, all equilateral energies are square energy levels, and these follow a specific numbering scheme or integer numbers, where we assign the integer numbers of 1 through to 9 the spectral colours of red through to black. Within the squared scalar energy geometries, which are again equilateral geometries, we find that odd number quanta come together. For example, 1 quanta is red, and the next level, the quantum level, has 3 in it, the third level has 5, and so on. They continue in a sequence of odd numbers, and these are odd numbered geometries are what we call bosons. They are a two-dimensional EM geometry, and because of their odd number of charged quanta, they always form a charged geometry, either negative or positive charge as a net charge resulting from the odd number of quanta. If you add sequential odd numbers together, you form square numbers. 1 and 3 forms 4. 4 and 5, being the sum of 1, 3 and 5, creates 9. 9 and 7, 16. So as the quantum level bosons come together to form larger scale energy geometries or increasing energy densities within measured units of time, they form together to form square numbered geometries. Again, it's one of the major points of Tetryonic geometry that the square numbers of physics aren't in fact square geometries, they are equilateral geometries. We can obviously denote the quantization of energy in a number of ways, but specifically within Tetryonics, what we do is we denote it with Planck's constant. In this case, bosons are denoted as being h nu geometries. They're all odd numbers, and where you see h nu, you know that it refers specifically to the odd numbered boson energy levels of scalar energy. Where these odd numbers come together, as we discussed, to form square numbered energy geometries or scalar energy, we then denote it as Planck's constant, or h nu squared. Again, this is done to differentiate between quantum levels and quantized scalar energies. Obviously, in the case of Tetryonics, this energy content can vary according to the kinetic energies of a particle in motion, or accordingly as we add energy to a particle's chem field, it will produce a linear momentum, which then can be associated via the mass to the velocity that this energy field creates. So there's a direct relationship reflected in the geometry of equilateral energies, and that relationship is for all velocities there's a required h nu squared energy within that geometry to produce that velocity. Again, if you see Planck nu, it refers to the quantum levels indicated by the various levels here, whereas h nu squared is referring to the scalar energy indicated by a large E. Obviously, as energy measurements, as energy is added to a system or to a charged geometry, it will affect the energy momenta content of that charged geometry, be it the charged fascia of matter, or be it the chem energy field of a particle in motion. In this case, you'll again note that we use n pi for all two-dimensional mass energies to distinguish them between two-dimensional energy fields and three-dimensional matter. If these were reflective of matter geometries, they would have T pi for Tetronic geometries, and they'd be 4n pi geometries. In this case, bosons are two-dimensional energy, so they are n pi energy, and the squared energy fields still remain two-dimensional energy fields, so they are n pi energies as well. The difference between the charge quantum levels and the scalar energies in this case is denoted by the colouring of the equation, and the fact that in the case of pi MAV, we're referring to just the quantized bosons, or the quantum energy levels within the scalars. As we're not measuring them per unit of time, we're strictly measuring energy. These geometries, as they have increasing number of quanta, we change the colours in accordance with the Tetronic colour code to reflect the number of quanta within each field. And obviously this colour code can be repeated with increased saturations to reflect higher and higher energy levels as we step through. Energy levels 1 to 8 are obviously the quantum levels within the atomic atom, where electrons are bound to the nuclei before they become free electrons. So they're the predominant colour code used in Tetryonics. All charged matter geometries, or T pi mass energy geometries, in the case of elements and other large-scale matter, are formed from deuterium nuclei. A lot more is explained in the quantum chemistry lectures regarding this geometry and how it comes together to form the periodic elements and larger scale compounds. But suffice to say at this stage that if we look at the geometry of deuterium nuclei, we can quickly see that they in fact form the same geometry and have the same electrical properties as Tesla's rotating synchronous converters. That is to say that they have the ability to store energy when a flywheel is inserted into the deuterium nuclei. They can absorb the energy as mass within their matter geometries, store this energy, and they store it both as mass within the deuterium nuclei fascia, as well as the mass increases within the deuterium nuclei, they increase the angular momentum of the leptons, or the electrons that are bound within the nuclei. The lepton itself, or the electron, is a three-pole rotating converter, a quantum rotor. It has three identical tetrions forming its geometry that are held apart by repulsive strong forces between their charged fascia. It has the same 12 pi geometry making it up as a quark. However, it forms a different geometry structure to that of a quark because of these repulsive charges between the fascias. That's what gives leptons a different name and a different physical geometry to that of quarks. Obviously, as I said, as the leptons themselves, the deuterium nuclei themselves combine together through the residual electric field forces of their constituent quarks to form helium nuclei, or to increase the energy levels of the deuterium nuclei themselves. You consider these, liken them to batteries, in that they store energy as mass within their geometry, and they can come together in side-by-side or anti-parallel configurations where the neutron can be viewed as a cathode and the proton can be viewed as an anode, with the electron obviously bound in the middle. The electron then has the ability to release energy, or release mass energy, over a period of time as spectral lines or as radiant energies. Where they come together one above the other, it is akin to a series configuration of quantum batteries. And again, if you were to put a light bulb instead of the electron across a single battery, it will glow half as bright as it would if you put it across two batteries. The same thing happens at the quantum level. As we mentioned, with the mass energies being stored in the fascia of the elements themselves, we can see here clearly in this schema, as we add the energy to the charged fascia, obviously the geometry of the fascia remains the same. But what does change is the wavelength of the Planck quanta as they're added. Again, they're added as odd-numbered bosons to each level to create square-numbered scalar energies or mass energies, where the energy is measured in a unit of time. It goes from being a scalar energy to being a scalar mass measurement. So obviously in this case we can now state the difference between mass energies as being just the unit of measurement, the measurement of energy per unit of time. And in the case of matter, we can show that with the standing wave geometries of energy forming tetrahedral geometries of matter, any increase of energy in these fascias will be spread out, has to be in square numbers, and again, if measured per unit of time, will give us the mass of the matter. The terms mass and matter are distinct terminologies and distinct physical properties within Tetryonics, clearly defined, and important that they remain defined for a full understanding of quantum physics right through to cosmology. And as I've mentioned, within Tetryonics we term two-dimensional mass energies as n-pi, because they can contain a large number of equilateral geometries, and we term matter as t-pi, or Tetronic geometries, and the T stands for n-pi, so they're always made up of matter quanta or tetrons. Obviously in the case of mass energies, each mass quanta has a charge, be it positive or negative, and they all combine within the matter geometries to give a net charge, again made up of positive and negative charges, but the final charge of the particle itself depends entirely on the charges that make up the geometry of the matter and the frequency of quanta within those charged geometries themselves. Obviously, as we increase the mass energies within the charged geometries of the matter itself, this has a direct effect on the angular momentum of the rotor or the electron within that matter geometry. The matter, or the deuterium nuclei in this case, has a 72 pi geometry of matter, whereas the electron only has 12 pi. It's considerably lighter, both in mass, similar or the same charged fascia geometries, but it's smaller, 12 versus 72. And as such, as the energy content of the deuterium nuclei increases, the electron will have an associated change in its angular momentum. This is brought about because the deuterium nuclei will increase the chem field of the electron, and in doing so the electron is bound, so it's no longer able to move in a linear direction. It's forced to rotate within the nuclei. Obviously the total nuclei is 84 pi, the combination of 72 and 12, and that geometry is the total geometry of any deuterium nuclei, along with the energy being the mass of the matter once it's measured in a time basis. You can reckon this to being akin to the way we store liquid gas at the moment. We store it as a weight measurement within the cylinders for barbecues and for caravans. The heavier the bottle, the more energy content it has. No different with quantum converters or deuterium nuclei. The heavier the nuclei itself, the more energy in its charged fascias, and the more energy that is available for release in various forms. Obviously these energies can be released as angular momentum or rotational motion of the electron itself, to the point where it can actually increase the chem energy of the electron to break it free from the nuclei. Obviously it can absorb and emit energies as photons of light or heat, blackbody radiation, and all this energy itself is stored as non-radioactive mass within the matter geometries. So a deuterium nuclei itself is a quantum converter. It not only converts, but it also stores energy as mass within its matter geometries. And one of the things we can do as we develop Tetryonic technologies based on the theory is we can build large macro scale versions of the quantum converters. We can then transfer energy into them, charge them up if you like, and use them to run houses, caravans, even entire suburbs, thus negating the need for overhead power lines or lots of coal-fired power stations. We can develop clean, limitless energy technologies, store it within the deuterium nuclei geometries, and then transport these and distribute them to wherever energy is needed as mass, and then release the energy on demand. As the deuterium nuclei get lighter and lighter, obviously the energy is being used up, and when they reach a certain point, we can swap them out for a brand new quantum converter. As we touched on, the protons and neutrons come together with the electrons to form the rest matter geometries of deuterium nuclei. You can see here we have the final mass of the matter, the N mass, where you see an N. Obviously that number is in reality multiplied by 1 by 10 to the 19 as discussed in quantum mechanics, but as a shorthand we just write it in green for the mass matter geometry, or mass of the matter geometry beside each element. We also show the net charge. In this case it's a 0 net charge with the electron bound. And then we can add energy in square or in odd numbered quantas, boson levels, to each charge fascia and increase its energy level. In doing so, within the atomic nucleus, we can step from energy level N1 through to N8. In reality, these are energy levels 25 through to 32. The energy levels of 25 through to 32 squared for the deuterium nuclei produce a corresponding energy in the chem fields of the electrons that bind with them. And these of course are energy levels 1 through to 8. So even though they're marked as 1 to 8 here for simplicity, they are in fact 25 to 32 squared, producing electron energy levels of 1 through to 8 in correspondence with these energy levels. Obviously the energy of the electron when it's bound is a kinetic energy, and we'll go on to show that it's not only just kinetic energy, but it's also a magnetic moment resulting from the energy in the chem field of the electron when it's bound. Obviously, if we add energy to the chem field of the electron, we'll increase its angular momentum within the nuclei, and that can cause it to jump from one nuclei or one atomic level to another, creating our familiar spectral lines within the periodic elements. But in all cases, it's odd-numbered bosons coming together to form square energy levels within the charged geometry of matter itself. As illustrated here, we have energy levels N1 to 8 within the atomic nucleus, which equates to atomic shells K through to R. They're all neutral deuterium nuclei, but as the mass matter of the deuterium or the deuteron nuclei increases, so does the chem energy of the electron, and obviously its angular momentum while it's bound. Should an electron be excited to the point where it breaks free of any binding position within the atomic nucleus, obviously this angular momentum from the chem energy becomes a linear momentum, and the electron moves off in a certain direction. This applies equally to antimatter as well as matter. The only difference between the matter and the antimatter, or the deuterons and the antideuterons, is the charges of the quarks, the charge fascia of the quarks that make up the baryons themselves. And of course, in the case of antideuteron, it will be a positron that binds to it, not an electron. But in all cases, the energy itself is stored as inert mass within the matter geometries, not inside the matter geometries. It's actually on the matter geometries. It is the charged fascia. Inside all tetrons, there is absolutely nothing. They are quantum Faraday cages. They exclude all radiation. As we've mentioned, as we increase the energy levels of the electrons from their rest matter configurations, or N0, from 1 through to 8, we're simply increasing the energy content of the chem field. When we reach energy level 8, we've added 13.5259 electron volts. If we go above this number, we're adding more energy to the chem field than is able to keep the electron bound to the nucleus. So it will break free, and again it will be a free electron and no longer go through quantum jumps. It will emit continuous spectra of light based on the energy, or in this case when it's free, based on any velocity changes. As the velocity increases or decreases, if it decreases from a set velocity, it has to release that energy as light. Obviously, the relationship between velocity and the speed of light is the linear momenta, and in the case of velocity squared, v squared, or nu squared, the quanta of energy, and the c squared geometry that's measuring, that the energy is being measured in to create mass, there's a percentage, and this is normally expressed as a Lorentz contraction for the velocity of the particle. As the velocity increases, we have to increase the energy quanta to create the energy momenta in the field to drive it at that velocity. So within any c squared measurement of the energy for the mass measurement, we'll have a Lorentz correction factor for any velocity. And again, it's important to note that in all cases, the mass matter geometry, or the mass of the matter geometries, is Lorentz invariant. All the energy that's added to a particle as it increases its velocity is added to the chem field of that particle. It's not added to the mass of the matter. So all the additional mass from acceleration, or a particle being accelerated, is contained as mass energy in this two-dimensional chem field, not within the matter geometries itself. Tetryonic chemistry goes through this in much greater detail, and obviously with the tetryonic chemistry we reveal that elements themselves are made up of deuterium nuclei, and the number of deuterium nuclei matches the atomic number of the element. So a Z number of 5 would have 5 atomic nuclei. A Z number of 92 for uranium, for example, would have 92 deuterium nuclei of varying energy levels comprising that particle. If you go back through the quantum chemistry lecture or download the book number 3, Quantum Chemistry, you'll see the geometries, both the side elevations along with the top elevations and all the exploded view of the elements of the deuterium nuclei themselves for each and every possible periodic element, or 120. Again, with those deuterium nuclei and with all matter, it is the energy content of the charged fascia that determines the mass of the matter. Any additional mass energy that's added due to acceleration is added to the chem field, not to the mass of the matter geometries. In the case of energy fields, the energy is always added in odd-numbered geometries or bosons, a two-dimensional charge geometry or exchange charge carrier. And in the case of matter, we have tetrons, which are the quanta of all matter. We have 12 pi geometries, which are quarks and leptons, and we have baryons that are 36 pi. These obviously come together to form the 84 pi deuterium nuclei that are in all elements. Again, the only difference in the case of quarks and leptons is the interactive, repulsive or attractive strong force between their charged fascia. And in the case of the various families of leptons and quarks within the particle zoo, again, the only difference is in the energies that go into creating them, their mass of the matter geometries or their kinetic energy fields. Obviously, two-dimensional energy geometries form a linear energy transfer. They store it in that fashion. Leptons have the ability to hold 12 pi mass energies within their geometries, while baryons can store 36 pi mass energy geometries. So baryons are far more efficient at storing energy than leptons, and accordingly bosons and photons are less efficient again, but they're effective in transferring the energy vast distances. Again, just a quick note here, N represents 1 by 10 to the 19. It's a shorthand within Tetryonics, where you see M alpha N anywhere, you know immediately that it's 1 by 10 to the 19 quanta, or a square number of quanta within that field. It's just the energy levels, the difference between quanta and N energy levels. And again, an important point is that it takes 2 quanta to form a frequency, a positive and a negative charge, to form a neutral photon set. So frequency is not equal to quanta. You can't say, as has been said in most textbooks, that Planck's E equals h nu equals Einstein's E equals hf for the energy, because one, h nu is a statement for the boson energy levels, the quantum levels of scalar energy. Hf is the energy of photons specifically. Again, if you were to divide the quanta up, you would find that they would end up with a half-numbered frequencies along the bottom, because photons are pairs of quanta, positive and negative, and you won't fit whole photons in at the base of these structures. They're all half. So that's why Tetryonics again stresses that h nu is the formula for quantum levels or bosons. H nu squared is the formula for the energy or the scalar energy of equilateral geometries. In the case of frequency, we're talking about boson pairs, photons. So again, they're different measurements for the same thing. It's no longer correct to lump them all together and just call them frequency, irrespective of the symbol that's used. As we've discussed, adding energy to the chem fields of electrons or any particles will create increased linear momentum for that particle. Or another way to say it is, if you accelerate a particle to a certain speed, its kinetic energies from that velocity will be all contained within the chem fields of the particle in motion, not within the mass of the matter geometries. You'll note that the mass of the matter in all these cases remains the same, 1.2 by 10 to the 20, or 12 charged fascia, each with 1 by 10 to the 19 quanta in each fascia. The difference between the charged leptons and the neutral leptons, which are neutrinos, is their mass energy contents of their charged fascia. They have identical physical sizes to each other. The difference being that neutrinos only have 1 quanta per charged fascia, so they're extremely light, whereas the electron and the positrons have 1 by 10 to the 19 quanta in each fascia. And again, this is covered in more detail in quantum mechanics and equilateral energies. The chem fields, obviously particles and motions, can be stylized using Tetronic geometries. We can just put a point particle in the center to indicate the net charge of the particle in question, and then we can use the equilateral triangle to indicate the kinetic energy and the associated magnetic moment of the chem field that produces the motion or as a result of the acceleration. Again, as the energy levels increase, so does the velocity of the particle in motion, and so does the energy quanta and energy momenta of that quanta within these fields. The more velocity, or the higher the speed, the more energy momenta quanta is contained in the field. And obviously, to change from one field to the other requires a change of the number of quanta, and they have to step through square energy levels, and they do so by releasing odd numbered quanta in the form of bosons. Again, just as the neutrinos differ from the charged leptons by the amount of mass energy in their geometries, we can also change the families of the neutrinos and leptons from ordinary leptons to muons to taus, simply by increasing the mass energies of their velocities, or the mass energy of their chem fields. By doing this, their relativistic masses will obviously increase as the velocity increases, and the wavelengths of the energy quanta within the chem fields will change in accordance with Lorentz corrections for the particle in motion. But importantly, the mass matter geometries will not be affected by any change in motion or any acceleration, deceleration of the particle. They are completely velocity invariant and Lorentz invariant, obviously, because of that. All the mass energy changes that occur, so frequency, the increase of frequency of quanta to drive the particle faster, and the associated wavelength contraction, all happens within the chem fields. Obviously, we can apply a standard formula for energy to the chem fields themselves. E equals mv squared. In this case, we're referring to matter, velocity squared. As the particle's accelerated, the chem field has to have sufficient energy to move that mass matter at the desired velocity. It does this by increasing the quanta within the chem field, the energy momenta quanta, and this creates a net energy momenta for the field. we can just use E equals mv squared for this formula. As you see up here, we've, instead of E, where we've specified that it's a chem field energy, we use matter velocity squared for the entire field, which includes the kinetic energy plus the magnetic moment that's created from its motion. And we can also relate that back to the frequency of the wave of the light that's produced through changes in velocity through Planck's constant. Again, it's probably more appropriate to, in the case of here, for a strict relationship to be exposed, to use h nu squared. But we can use hf if we wish to directly relate it back to the frequencies of the spectral lines produced through the acceleration or deceleration of electrons within the nuclei. And that's what's indicated down the bottom here. A rest matter electron has no chem field whatsoever. It just has its charge and the mass of the matter geometry. As the electron binds to deuterium nuclei in various atomic positions within the elements, its chem field is changed accordingly, or the energy content of its chem field is changed accordingly. And the linear momenta that's created from these energy momenta quanta, in each case, will try to accelerate the electron in a straight line. As they're bound, it's unable to do it. So what happens is it creates a physical quantum angular momentum, or just an angular momentum for the electron within, while it's bound to the deuterium nuclei. If sufficient energy was added to its chem field to increase it past any more than 64, say 65 or more, it would exceed the energy that binds it to energy level 8, and it would break free. It would have enough energy, or kinetic energies, to overcome the coulombic attraction of the proton in each of these energy states. And at that point, the angular momentum would cease being angular, and it would be a linear momentum, and the electron would fly away from the atomic nuclei. This is obviously a picture showing the electron bound within the deuterium nuclei and its chem fields. The magnetic moment of the chem field is always related back to the nuclear magneton to describe whether it's an up or down spin or a parallel anti-parallel spin that's produced. There is no physical up or down direction. It's always a measurement of the Bohr magneton with reference to the nuclear magneton of the particle itself. Again, these energy levels are pictured here with their associated linear momenta, and you'll see in each case that the charged geometries of the matter and the mass of the matter in all cases does not change. What's changing is the energy content of the chem fields. Obviously they're coloured, they follow the colour code here for tetronic energies, tetronic numbers. In fact, a yellow field would have 9 energy quanta, or 9 by 10 to the 19 energy quanta within it. And as indicated here, we've given that amount of quanta, and we've also calculated it as an electron volt to show that it matches up with current theories. We can stylize this as a nice schematic for an electron with varying quantum levels of energy, and we can show using this with circular lines between the energy levels that as the electron drops from N8 energies down to whatever N1, N2, N3, it does so by releasing energy or emitting energy from its chem field. This is not on the charged geometry of the matter, it's purely the energy in the chem field. And accordingly, if it wants to jump up from one level to the other, it must absorb energy in order to go from one energy level to the other within the atomic nuclei. As we note here, it is for illustrative purposes only. It's not reflective of where the energy is stored. It's only a quick schematic to help explain the changes or the transitions between energy levels. As an example here we have uranium, element 92. You can see we have a polar view of the element as well as a side elevation. The exploded view shows us all the individual deuterium nuclei that make up element 92, uranium. And you can see that the physical element of uranium is far more compact than its exploded view if you were able to pull the element apart. And accordingly, within the element itself, we have the various energy levels and nuclei that electrons can bind to. Any missing electron in any of these positions will result in the uranium atom taking on a positive charge, in which case it will try to equalize under the second law of Tetryonics by attracting another electron from somewhere else. Say for example a level 6 or a p-shell electron was ejected, there'd be a free spot. The charge of the uranium atom would be such that it's positive. It would then attract another electron, and when that electron bound to that free position, it would be forced to have a energy level of N6. If it came in as a N1, it would automatically have the energy in its chem field increased to N6 so that it becomes stable again. And this is how the uranium atom releases its energy naturally over time. The energy that's stored in the mass of the matter geometries is released slowly through the electrons and their chem fields and angular momentum when they're bound to the atom itself. Of course, if there's a release of sufficient energy, these electrons can pop off as beta radiation. We can also look at the uranium atom from the aspect of the element families themselves. Again, you can still see the sp, d and f orbitals that are produced by the electrons as the atom itself rotates, just as we had the energy levels highlighted here in the previous polar view, where energy levels 4 to 8 were clearly visible, but 3 to 1 were hidden, looking down on it. We again have the same thing here, but in this case it's the elemental properties that are on display via the color code. In both cases we can see the molar mass of the uranium atom. Again, this molar mass is the absolute rest mass matter for uranium atom. Any additional mass above this amount is a reflection of increased energy levels somewhere in the atom, be it within the mass of the matter geometries, or be it in the form of black body radiation or energy of motion. But the absolute molar mass, rest mass of the matter for uranium atom is what's calculated here. We obviously have the charge geometry. The 92 elements give us a total of 7,728 charged geometries in the nucleus. And knowing the rest matter, we can in fact calculate the absolute rest mass, and we can calculate the stored energies in the charge geometry that result from these quantum levels 1 to 8, or 1 to 7 in the case of the uranium atom. The difference between these energy levels from 92 rest deuterium atoms gives us the stored kinetic energy within the mass geometries, or what's commonly termed chemical energy within the element. Again, if you were to divide this number by the by 22,500 for a neutron, you would quickly calculate this number of supposed extra neutrons that have always been added to elements to account for their mass as a result of chemical models always having equal numbers of protons and electrons, but then accounting for the excess mass or the differential as excess neutrons. The chemistry lectures clearly identify what's happening here. It's not extra neutrons. There is, for every element, the protons, electrons and neutrons equal the element's number. The excess mass is a result of the quantum levels of the deuterium nuclei itself. And again, spreadsheets are available, or you can go through the chemistry ebook and you can see the individual calculations for each and every periodic element. Of course, we can strip out all the deuterium nuclei, and that leaves us the electron orbitals for each element. We can see, obviously, again, we can see energy levels 4 through to 8, with 1 to 3 being hidden below energy level 4, but in exactly the same position. And again, with each element, you can see the numbers written in the electron positions. The colours indicate the energy levels of the electrons. The numbers indicate how many electrons in that position are located in that position. So in the case of here, where we have 7, there's obviously 6 more electrons down the side elevation down here. You see 1, 2, 3, 4, 5, 6 are below that 7th one. So again, the schema in both cases have these numbers, so you can quickly look at these numbers and add them up. All these numbers will add up to 92, so they reflect how many electrons are in and the energy levels of those electrons, should you wish to accelerate any of them away or create spectral lines and calculate for the spectral lines for each element. Obviously, as well as a polar view of the electron configuration, we can generate a side elevation of the electron configuration and split it out slightly into the shells of electrons within the element itself. These obviously correspond to spectral line arrangements or transitions between one energy level and the other by electrons. And the only time that there's a distinct difference is where you have up and down spins. Again, the up and down spin is calculated by determining the orientation of the magnetic moment of the Bohr magneton of the electron, and comparing it to the element's nuclear magneton or magnetic moment. This will then give us a up or down spin. They do come in pairs as per Hund's rule, and they're indicated here on the illustrations as red for up or parallel and black for down. Again, all these transitions give us the spectral lines and the matter content, or the raised quantum levels of the deuterium nuclei within the matter geometry of the elements, gives us the total mass of the element itself, or the molar mass. The difference between the differing angular momentum of the electrons as they bind to various positions and transition between these positions gives us the spectral lines. And over time, if left undisturbed, these electrons spinning at their rate will also seek to reduce the energy levels of these atoms through decay processes, either through photons or beta decay, whatever. Various methodologies, we'll cover them shortly. Again, Tetryonics accounts for the atomic nucleus in a number of different ways, and accounts for not only the geometry of the element, its rest mass matter, or rest mass energies of the matter geometries, but it also gives us an exact value in the case of rest mass matters, the exact value of the stored chemical energies or stored chemical energies within the element. Tetronic elements, or Tetronic chemistry itself, goes through every single element. You see them all listed here. We can give a polar and side view for every element, along with the exploded view of the deuterium nuclei and the energies that make them up. But they all range from element number 1 being deuterium through to element 120, and obviously we also have element 0, hydrogen. Traditionally, hydrogen's been listed as element number 1. Tetryonics shows that it should actually be deuterium, as deuterium is the building block of all atomic elements, not hydrogen. And again, within this equilateral geometry, even though it's only a schema for arrangement, it does indicate the energy levels of the respective elements as they add their s, p, d and f orbitals and increase their energy content within the nuclei. Again, all these elements are to scale one to the other, and that's again something unique that Tetryonics offers. It gives us the radii, if you like, of all elements, and we could of course rearrange this table here to show the side elevations of all elements as well. As we increase the mass energies of all these charged geometries for all the elements, we of course increase the angular momentum of the electrons that are bound with them, as well as the mass of the final element as well. What you see listed here is the first 20 elements, along with their various quantum levels 1 to 8 for each of these elements. As we raise the energy in the charged geometries of the matter, we of course increase the mass. And using these calculations, and again dividing them back by the matter geometries, we can quickly calculate the excess or the increases of mass. Normally, as we've mentioned, these are accounted for as being extra neutrons bound to the atom, giving us the radioactive isotopes of each element. In fact, what is happening is that the energy levels, or the mass energy levels of the charged fascia themselves is being increased. So once the energy levels increased, obviously the atom will try to decrease it back down, and it does this by emitting particles, be they in the case of large elements that can emit alpha decay particles, actual chunks of the atom itself, or it can release electrons. When it tries to excite the electron and get rid of the energy, it can release it slowly over time in the case of radiocarbon dating, or if too much energy is released, it will physically eject the electron. The energy in the chem field will be sufficient to create a linear momentum to break it free of the coulombic attraction, and it will be a free electron in beta decay. Or in fact, it could just release all the energy as a big burst as a gamma decay process. In all cases, as we increase the energy, in this case hydrogen atoms, as we increase their energies, we highlight them with the changed energy levels with the colours that are appropriate, and we also show this colour on the bonding points for the elements themselves as well. As we mentioned with radiocarbon dating, what we see here is the carbon-12 or graphene form of carbon, and then doing the calculations and raising the energy levels, we see that the base carbon atom, carbon-12, has a molar mass of 11.996. Again, chemistry explains why we have this exact mass instead of 12, which is the normal accepted amount. It's because with Tetryonics we can calculate an exact rest matter or rest mass for hydrogen and compare that to Avogadro's number. We can also calculate an exact mass for 2D planar Planck quanta, and applying this throughout all energy geometries gives us a rest molar mass of 11.996 for carbon-12. Carbon-12 is a stable carbon atom. It has a rest mass matter, as listed there, of 270,072 N quanta, and it's the ground level. You can't get a lower energy state than this for carbon-12. But as we increase the mass energies of the charged fascia, obviously the mass of the particle itself increases, as does the angular momentum of the bound electrons within the nuclei. In doing so, we obviously jump from level 1 to level 2 and 3, and as we do the calculations for the mass of the matter geometries, we discover that there's excess kinetic energies in both cases. A bit hard to see on this page, but you do the you calculate the energy, the stored kinetic or the chemical energy for each isotope, and you discover that there's enough energy to in fact convert to mass, and that mass would be equivalent to an extra neutron in the case of carbon-13, which is why it's called carbon-13, and an extra 2 neutrons in the case of carbon-14. In fact, there are no extra neutrons in both cases, as you see here, 504 charged geometries, 504 charged geometries, and 504. Again, the matter geometry is invariant. What has happened is, within those matter geometries, the mass energy has increased, and accordingly the energy within these, the mass energy within these isotopes is higher, and the atom, according to the second law, will seek to reduce this excess energy content by increasing the angular momentum of any bound electrons. These act as tiny quantum rotors, so obviously the higher angular momentum of these will release energy over a set period of time. It's predictable. It's no different than any other rotor that's spinning or any flywheel. They release energy and use it up at a certain rate. In this case, in the case of carbon-14, it's got a half-life of 5,730 years. It's a very predictable decay rate to decay back down, and in fact what happens in all living organisms is as a byproduct of them consuming energy and moving and having physical exercise, the carbon atoms within their structure absorb energy from the biological processes, and over their lifetime a large percentage are sitting at carbon-14 and are maintained at that level. As they're trying to release energy, they're obviously also absorbing energy due to their quantum converted geometries. So they all become this level. When the organism dies, then there's no longer any biological energy feeding into the system, and it starts to bleed it out at a set rate, allowing us to radiocarbon date carbon atoms as they degrade from this higher energy level down to the lower energy level. But in all cases, these carbon-12s have 6 protons, 6 neutrons, and 6 electrons. There are no extra neutrons in this process that are released. This again clearly illustrates what we've just discussed, and in this case it highlights the geometry of carbon-12 versus the periodic carbon. Same structure, again you can see it's 504 in charged geometries, so it's the same element. The difference is in how the deuterium nuclei came together. In the case of carbon-12, there are two N1 two N1 deuterium nuclei in the s orbitals below the N2 energy levels. So we have 6 elements, 2 which you can't see here, which are energy level 1, and 4 at energy level 2. Whereas in carbon-12, all 6 deuterium nuclei are at the same energy level. They're bound in this position, and you'll see if you look closely that there's 3 protons facing up and 3 neutrons facing up, form a Star of David, if you like, within the geometry of carbon itself, as exemplified at the top right. As we increase the mass energies of these charged geometries, we accordingly increase the total molar mass of these isotopes. And again, where you calculate these, whether you calculate them as quantum equilateral geometries, as we do here with Tetryonics, or whether you calculate them as energies, it makes no difference. When you recalculate this or divide this stored kinetic energy or chemical energy by the mass or the energy that's required to make neutrons, you see that in carbon-12 there's almost enough for another full neutron, simply by raising the energy level of the charged geometries from N1 to N2. You get almost a full neutron worth of energy. Again, the reason why you detect a full neutron is that you never have the carbon atom at absolute zero with no background, no blackbody radiation or no kinetic energy. It's always some motion within the atoms itself that are being measured. So any excess energy from the motion or the blackbody radiation will add to the mass energy that's being calculated for here. Again, as we step to level 2, you see that we have enough for 2 neutrons worth of stored energy. We step to energy level 3, that was, to energy level 4. We have sufficient for just over 3 neutrons worth of mass energy. Step to level 5, we have enough for 4.2 neutrons. And again, energy level 6 is enough for 5 neutrons worth of mass energy. So you can see the direct relationship, and that the need for excess neutrons is no longer valid. In fact, the geometry remains the same throughout. What changes is the energy level. This in fact is reflected in the mathematics of chemistry, but it's never been realized to the full extent like it is within Tetryonics. Tetryonics takes the energy levels and paints the full picture, if you like. Again, we've done the same illustration here, highlighting 6 deuterium nuclei at the same energy level, and we've increased that energy level for each shell and calculated the atomic numbers or the isotope numbers for the elements beside it. We can then plot for each and every element the number of protons against the number of neutrons for each element, and obviously as the elemental number is equal to the deuterium nuclei that make it up, this plot will be a straight line, because each deuterium nuclei has the same number of protons to neutrons, and again the same number of electrons that bind to them within each nuclei to create the element. This straight line deviates obviously from the curve plot of unstable isotopes or nucleotides that we currently use, and that deviation is simply the result of mass energy added through these quantum levels within the element itself. As you get larger and larger elements, you have increasing energy levels and increasing number of deuterium nuclei at differing energy levels within that atom. This is a major departure from current theory, and all the textbooks will obviously have to be changed in order to recognize the fact that the deuterium nuclei is the basis of all periodic elements and all elements in general, and that this plot is a straight line. But it is a major breakthrough in understanding this curved relationship as being just the relationship of the energy or the mass energy content of the charged geometries, not excess neutrons as has always been the case. Obviously, where we have raised energy levels within deuterium nuclei, these nuclei will seek to reduce this energy to form a stable configuration. And they can do this in a number of different ways. They can release loosely bound deuterium nuclei in the f orbitals, for example, and they can fly off either as pairs or as single deuterium nuclei to bind with other nuclei to form helium, or they can excite the release energy into the chem fields of the bound electrons to the point where the electrons themselves break free, or they can release energy in bursts as gamma radiation, bearing in mind that these energy levels can have sufficient for 5, 6, 7 or 8 neutrons worth of neutral energy, so it's no problem for them to create gamma rays through the release of this energy in a burst, and equally it's not a problem for them to form some of these gamma ray energies or photons into particles such as neutrinos, or in fact it can create electron-neutron pairs, and we'll discuss these processes in detail as we proceed here. As a side note and of interest, completely by chance, the symbol for radioactivity happens to closely mirror the physical geometry of leptons. I've done some research to try and find out the genesis of this symbol, and I haven't seen a complete explanation as to where it came from or how it was developed. But obviously the similarity between it and a lepton is remarkable, and given the role that leptons play in radioactivity, it's even more remarkable. Just one of the few coincidences in quantum mechanics. And again, that same geometry is apparent in Tesla's work for rotating converters or flywheels within his electromagnetic motors, and why he developed three-phase power. Looking at the decay processes, there's obviously three decay processes: alpha, beta and gamma. The alpha ones being the emission of deuterium nuclei that form helium particles. Then there's beta decay, which releases leptons, be they neutrinos and or positrons and electrons. And there's gamma ray bursts, as we've discussed, or gamma ray production. Of note, at the top left-hand corner here, we have a box titled Transmutation process. It's commonly assumed, for historical reasons, that neutrons are formed from protons absorbing electrons, and that's why they, in current textbooks, the neutron is heavier than the proton, because from an historical viewpoint, the neutral charge was explained as resulting from protons and electrons being bound together. This is again repeated where they describe neutron stars and the like. And it was also decided that this was the case purely because a unbound neutron or a free neutron will rapidly decay into a proton and electron. So it was deemed sensible at the time to assume that this process was in fact the reverse of the process that created it. Tetryonics in fact shows that this is not the case. In the case of neutrons, you have 12 positive and 12 negative charges of the three quarks that make it up. Neutrons have 24 positives and 12 negatives, and electrons have no positives but 12 negatives. If you add the proton and electron together, you'll quickly see that you have 24 positive and 24 negative. It's impossible for these 24 positive and negatives to be generated from solely 18. Conservation dictates that that's clearly not what's happening. In fact, what Tetryonics shows is that the free electron, when it's detached from the nucleus, is within a very short period interacted with by free neutrinos in the environment. These neutrinos stream from the sun or other nuclear processes, but predominantly from the sun in our environment. And when you add the 18 positive and 18 negative charges of the neutron to the 6 positive and 6 negative charges of the neutrino, you in fact have 24-24, which then will allow the creation of protons and electrons from that. Of course, these neutrinos have to have high kinetic energies, mass energies, in order to account for the proton and the electron's mass energies. So you'll find that these are muons in most cases, or something similar, muon electrons. Obviously, as you create these particles, they have to have kinetic energy as well as their mass energies in order to be moving along and maintain the conservation of momentum as well. In the case of the other three particle decays we've mentioned, obviously deuterium nuclei or deuterons combine with electrons to form helium. There's various processes for that we'll discuss shortly. And the neutron decay process, a single neutron, should it decay, will produce either 3 electrons or a positron electron and a neutrino. Sorry, is that 3 neutrinos? Positron, electron and a neutrino. In all cases, just like chemical equations, the charge, the net charges of the elements must balance on both sides of the equation of transformation. So if you have 1818 in the original element, or the elements that are combining, the particles that are combining, you must have decay particles that add up to the same charges and also have mass matter plus kinetic energies that keep the conservation of mass energy on both sides of the equation. So we get 2 possible decays for neutrons. And with gamma ray production, obviously what's normally taken as a neutron in the element itself, particularly radioactive or unstable elements, is in fact stored mass energies, and again they're released as gamma rays, but as they're released as gamma rays, the mass energy of the system obviously changes, and sometimes this is noted as the loss of a neutron, when in fact it's the loss of a neutron's worth of mass energy from the radioactive or unstable element. Looking closer at the alpha radiation, obviously we can see that the 2 deuterons, in this case positive charges, will come together to form a helium. And in the case of helium, they'll need to create a neutral helium. So if you add up again the charges on these particles, you'll find that you require 2 electrons to bind as well. These may be ejected from the unstable element as complete deuterium nuclei with the bound electrons, or they may be ejected without electrons or at different energy levels. And obviously they will come out at different energy levels. Most of these, the first ones to eject, will be F orbitals, which are energy levels 4 and 5 within the atomic nuclei. So they'll come off as energy levels 4 and 5. They'll seek to release energy through the quantum rotor of the electron and through other energy processes, either through kinetic energy of motion or through black body radiation, heat, light. Again, they have their own decay processes, but they will form, when trapped, they'll form helium nuclei. And again, all the mass matter amounts are reflective of N levels and of absolute rest mass matters. They exclude any kinetic energies. But obviously the equation must balance for conservation of energy as well as conservation of charge in all cases. In the case of beta decay or lepton emissions, obviously a similar process happens. The nuclei is seeking to release energy. It can do so slowly over time in the way of spectral lines and transitions, or it can increase the energy of an electron to the point where it breaks free, in which case the particle will be ejected with kinetic and linear momenta in a specific direction from the unstable element. Or accordingly, in the case of neutrinos, it could eject a burst of energy that forms the neutrinos themselves with kinetic energy. Obviously, neutrinos, being neutral particles, can be formed out of the neutral particles of stored energy within the mass-matter geometries. Again, if we look closely at the neutron decays, or the chemical energies that are stored within the elements, it's just a shorthand where we list neutrons here. Obviously, it's the amount of energy that's of concern. We have a neutron's worth of energy. For example, in the case, if this was uranium, we would have 72 protons and electrons, 72 neutrons, but there'd be an excess number of neutrons that have historically been drawn that are in fact they are stored energy. They're not physical neutrons, so we can list them as a neutron. And again, we still have conservation of charge as well as conservation of mass energy in the decay process that releases this energy from the nuclei. Obviously, of course, same process occurs if you have a free neutron. It can break down into, or via interaction with a neutrino, to give us protons and electrons as decay particles as well. Gamma radiation can be emitted, which is just an extreme form of releasing a large amount of excess energy at once. As we've said, there are neutrons worth of energy stored in these atomic nuclei. That is why nuclear energy is able to produce vast amounts of energy. You can consider these elements, such as uranium and plutonium, as glorified coals or embers of campfires. They have excess heat. You can bunch them all together and they'll radiate their excess heat until they drop down to a certain energy level, in which case then they're radioactive waste. So the nuclear industry, fission industry if you like, can be deemed as an advanced form of gathering the campfire coals together to create energy for our technology. Where the chemical energy is released in a burst, obviously can be released as a gamma ray. Gamma rays are made up of photons of energy. The wavelength of the photons is determined by the frequency of the gamma ray emitted, and it follows a straightforward formula, E equals mv squared again, just like kinetic energies, except there's two charged particles. Obviously, gamma rays are photon or EM waves with photons. They radiate bidirectionally. So if we want the energy, we obviously just have to account for two masses moving at the speed of light, because that's their velocity in a vacuum, and we can relate that using Planck's constant to the frequency of the gamma ray that's produced, or the frequency of the light. Again, we can also relate that back to the quanta for the charge geometry of the atom itself, of the photon itself, EM waves. We can use the unified field equation for energy, as we have done, and we've shown that the Planck's constant, energy can be written as Planck's constant, nu squared for squared energy levels. Of course, Planck's constant itself can be broken up into mass alpha, or mass by quantized angular momentum, the equilateral geometry of masses. Or it can be also expressed in the classical form of mass velocity squared. Again, the unified field equation in Tetryonics clearly states which way or how this is written out, so as to be able to be read either way. It's important to remember this, because if you're not familiar with it, you'll at first look at this formulation for energy and wonder what the units are, and then in attempting to assign values to alpha, you'll be very confused. In fact, alpha per c squared is charge, or per unit per the quantized geometry per c squared electromagnetic field is charge. The angular momentum, or the geometry again with the mass, is Planck's constant. Again, these all relate back down to mv squared for single charge fields, or Planck's constant nu squared for the quantized energy fields. In the case of neutron decay, as we've discussed, it relies on the interaction of neutrinos with the free neutron to create the transmutation process that produces the proton and electron that's observed as the decay particles for the process. Again, we have 24 positive, 24 negative on both sides of the equation here, or the transmutation process, and we can follow this through and find that it's not only protons and electrons that are produced, but there's a whole range of particles. Obviously, so long as the charges balance out, we have the particle breakdown of what it can produce, and then obviously the mass energies also have to balance, which will then give us the mass energy and the families of the particles themselves, along with their kinetic energy or velocities of motion for each particle. Obviously, from a 24-24 combination, we can produce 2 positrons and 2 electrons. We can produce a positron, an electron, and 2 neutrinos, or just 4 neutrinos from that combination. Or we can convert the entire mass, the entire matter geometry, into radiant mass energies, i.e. convert neutrons into radiative light or heat energies. Noting, of course, that matter, unlike mass energy and charge, is not conservative. So there's no requirement to conserve mass geometry, or matter geometries, I should say, but there is a requirement to conserve the charge of the matter geometries. The charges must match up both sides of the equation. There is no requirement that they have to be mass or have to be matter geometries that are produced. They can in fact go from matter into just pure mass energies. Again, just a footnote down at the bottom right of the page, highlighting what we've discussed previously about the differences between classical modelling of elements, or protons and neutrons particularly, within atomic elements. It's, as we've noted, it's often been claimed that the neutron is slightly heavier as a result of it being created through the absorption of an electron with a proton in order to create a neutral particle. And of course, this additional mass has been factored into all the equations for elements for over a century now. Tetryonics shows that this is not the case, that the matter of a neutron is in fact the same as that of a proton, and the geometries are identical. They're triquark geometries. They're specific geometries. In the case of a neutron, it's a down, up, down geometry. In the case of a proton, it's an up, down, up geometry. Not up, up, down, up, down, up. They are symmetric in all the ways. To combine up, up, downs is impossible because the two positive charge facies of the ups will not combine. You need the down negative charges, or the negative charges of the down, to create the binding or the strong force. In doing that, obviously we have a neutral particle of 1818 and a positive particle of 2412, or a positive 12 and a neutral particle, the positive 12 being the exact opposite of the negative 12 of the electrons. They're all identical to the elemental charges, the only difference being a multiple of 12 to reflect their geometries. But most importantly, despite the difference in net charges, they are identical geometries to each other. And in fact, it's the combination of these two geometries that create deuterium nuclei. Obviously, as free neutrons interact with neutrinos in the environment to form neutron decay processes, the same can be true for protons. And again, looking at the proton decays that are possible, you can see the interaction. And again, we have 1318 where protons interact with neutrinos, and we have a number of different decay paths that are possible from that process. Most of this interaction takes place within the nuclei itself and results in beta and gamma decay paths. And again, just stressing that protons plus 12 net charges are not the same as neutrons, which are neutral net charges, but they are identical geometries and mass matters to each other. There is no difference in the mass matters or the energy contents of the charged fascia, and there's no difference in the geometry, save the charge arrangements themselves within those geometries. Obviously with Tetryonics we can now model all the elements, not just uranium, but every single element in terms of its energy levels, its charges, its mass, its absolute mass, as well as its stored kinetic energies that have been normally accounted for as excess neutrons. We can draw physical models of all the elements, and you can see how these elements could be mistaken on the macroscopic scale as spherical geometries. In fact, they are not spherical, they are all irregular shapes as a result of their equilateral mass energies and charges. But we can further a lot of our quantum chemistry through the understanding of these charge arrangements and the interactions and the differing energy levels that create the elements themselves. In fact, Tetryonics models these to a great degree. And once we understand these geometries and the relationship between mass, energy, and overall rest matter, and the stored chemical or kinetic energies, we can use this in various ways to correctly model fission processes and to reveal additional processes that we can tap for clean, limitless energy. Obviously, in the case of fission, we can show clearly that uranium, or element 92 in this case, has 7 energy levels and a total of 92 deuterium nuclei in its elemental configuration. What happens is, with the injection of a slow neutron, or a neutron with a small amount of, or a low energy, a chem energy field, the neutron will slam into the unstable element, and what happens is the weakly bound valence nuclei, if you wish, or the outer nuclei that aren't so tightly bound, fracture away, leaving the core electron configuration, which has much stronger energy binding, or binding energy for the configuration itself. That's why it's the core electron configuration. It's the central configuration of electrons where it's more tightly bound. The core electron configuration in the case of uranium's barium, and obviously these are already at a stable energy level. They are the barium barium element itself, surrounded by higher energy deuterium nuclei to form the uranium. With the fracturing process, or the splitting of the atom, the deuterium nuclei will move away, but they'll be quickly drawn back through the residual E-field interaction of their constituent quarks to form a common elemental configuration. Of course, they'll still have their higher energy levels, so it will form it'll try to form a stable configuration, but it will have all these raised energies. It will seek to create a stable element by releasing these energies in one form or another through the various decay products that can release energy through. The element it's trying to reach in a stable configuration in the case of uranium is krypton, and krypton and barium being the main byproducts of fission processes using uranium. The released energy, of course, can be calculated. We know that the mass matter of the barium hasn't changed because it's a stable configuration. We know that the released nuclei of varying energy levels, which we know the energy levels of from the Tetronic geometry of uranium, we simply take away the barium core, will be of specific energy levels out in energy levels 4, 5, 6, 7, 4, 5, 6 and 7. They'll come together and we know what the final energy configuration of krypton is. There are sufficient nuclei in both cases. Obviously the core hasn't changed, there's sufficient free nuclei of a raised energy level to form krypton. So they form again to form the krypton element, and they release the excess 4, 5 and 6 energy levels to form energy levels 1, 2, 3 and 4 of krypton. We calculate for this energy release, and we see that there's enough there for, in fact, 12 rest neutrons, or 12 rest mass energies of neutrons worth of mass energy, or just over 11 giga-electron volts released in that fission process. So again, Tetryonics gives us a much clearer picture of not only the fission process itself, but the release of the energy in the process. Obviously, this energy that's released does not necessarily have to be released as heat. It can be released in the form that forms neutrons or other decay particles. And in fact, that's what we see in fission. We see excess neutrons. We see approximately 3 neutrons created for every collision out of the 11 that are possible. And we also see neutrinos and heat being generated in the process as well from the stored kinetic mass energy of the geometries, matter geometries, or again, this can be retermed as the stored chemical energies in the uranium element itself. Professors Pons and Fleischmann announced a breakthrough back in 1990s of cold fusion, where palladium was able to release a huge amount of energy on the desktop, far beyond what should be possible using current understanding of chemical processes. Using Tetryonics, starting with palladium, working back to the krypton that was produced, we see that again it's a very similar process where the core electron of krypton is stripped away or broken away from the palladium. This is done by raising the energy levels of the weaker bound valence electrons, or valence nuclei more appropriately, within the palladium atom. By increasing their energy levels, they will fracture away, and once they've broken away, we'll have the krypton revealed, but these deuterium nuclei will be free to either recombine as another element or to break down into deuterium nuclei, or to lower their energy states to lower energy deuterium nuclei, or form other elements. In doing so, we can quickly calculate for the deuterium nuclei at their energy levels that are stripped away to give us the core krypton configuration, and we see quickly that there's 114,000 quanta, n quanta I should say, or the equivalent 4.7 giga-electron volts worth of energy that's released in this process. Again, that's roughly equivalent to 5 neutrons. Using the classical model, the model of quantum mechanics up until now in chemistry, you would expect a neutron bath to be emitted when all these electrons worth of mass are released in this process. And in fact, that's what they claimed. They said to release this amount of energy in the process that was described by Professors Pons and Fleischmann would result in them suffering a severe exposure to neutron radiation as the neutrons were released away. In fact, Tetryonics shows that there would be no neutron radiation released in the process because there are no excess neutrons in any of the large atomic nuclei at all. There's always equal numbers as a result of them being deuterium nuclei. And again, this energy can be released in a number of forms. It can reform back into neutrinos. It can form electron-positron pairs. It can form neutrons themselves, although these processes of the heavier elements are much less likely because you have less than a third of the energy released of what's released in fission being released in this process. It would be more appropriate to reterm cold fusion into either cold fusion or cold fracking or something along that line, where it's more descriptive of the process that's going on Cold fission is probably the most appropriate because it's still a fission process and it's cooler than classical uranium fission, as noted by the energy levels between this and that of uranium fission. One of the statements of the scientific panel set up to investigate cold fusion, when it was proven to be difficult to repeat the process, stated in their summary that, and as quoted here, that nuclear fusion of the type postulated would be inconsistent with current understanding, and if verified would require theory to be extended in an unexpected way. Well, there's a number of problems here. Firstly, it obviously isn't fusion as currently formulated within scientific literature. It is in fact a fission process. Secondly, Tetryonics obviously rewrites the history books in an extended and unexpected way so far as physics and chemistry is concerned. It gives us the charge geometries, the mass matter arrangements of rest mass matter arrangements of all the elements in order to do these calculations quickly and simply. And it gives us a completely new understanding of the processes at work. In doing so, the experimenters should no longer be hamstrung by the present day assumptions that it's a fusion process, and that through the use of Tetryonics we can in fact develop a number of ways of achieving this process on the benchtop to give us a source of clean, limitless energy, or limited energy in the case of palladium to krypton fission processes. But all things aside, Professors Pons and Fleischmann are due a overdue apology and recognition of their work in this field. Had they been followed correctly and had the process been repeatable, no doubt changes to the quantum chemistry and to quantum mechanics would have been forced on the industry through this process. It may not still have been as thorough or as accurate as Tetryonics, but it would have been forced to change. In fact, what we see here is a case of science being hamstrung because it was easier to accept that it may not be possible or to require a radical rethink that wasn't available at the time. We can also produce a similar form of energy via sonoluminescence. Again, this has been attempted to be explained a number of ways in modern quantum chemistry and modern physics. What happens in most of these experiments is that a flask of water or similar substance is bombarded from several directions with high energy sonic pressure waves. They come in at various angles, but Tetryonics shows that standing wave energy geometries are tetrahedral. If you bombard the standing wave energy geometries with sufficient energy, they will collapse. They are a solid geometry and resist forces against them in a very efficient manner, and that in fact is what gives us the solidity of matter, not the repulsion of electrons. All matter owes its solidity to the quantum geometry of its matter quanta, the tetrons. But if subjected to sufficient pressure, they will collapse. Obviously, when the tetrahedral standing waves collapse, they go from being matter to radiant mass energies, as we've discussed with fission and other processes, decay processes. It's no different. Matter itself is not conservative, but the mass energy and the charge is. So, whatever the byproducts are, when the matter quanta is collapsed, in the case of water, the easiest ones to collapse are obviously the electrons and or the hydrogen nuclei. Only an examination of the byproducts produced would tell us what the exact breakdown is, which elements are collapsing first, but they would be the easiest ones to collapse. As the tetrons, which form all matter geometries, collapse one by one, what's left is a a region of nothing, because inside each matter tetryon is absolutely nothing. They are quantum Faraday cages. All the mass and energy of the matter geometry is stored in the tetrahedral fascia, not within the matter as a gas or energy. It is all stored on the equilateral charged fascia. So as they collapse, they leave behind this void, which obviously the water will collapse the fill into over time. But for a brief instance, you'll get a flash of light as the matter is converted into energy and radiates away from the point, and it will create a sphere or a region where that matter was until the water or the substance can collapse back in. And this is exactly what we see in sonoluminescence. Obviously the name's derived from the fact that sound waves, sono, produces the luminescence or the light in the center. And in fact, Tetryonics describes this process clearly as simply being one of the first steps to clean limitless energy. We can use cold fission, or we can use sonoluminescence on the desktops as a cheap, repeatable and clean desktop way of converting matter into energy. And in fact, it's the first step in creating a new technology based on matter to energy conversions. It's an important step, and figuring out the charged geometries of matter was equally important in moving forward in this breakthrough. Obviously, whether it's termed cold fusion or cold fission is up to academics in the field to discuss and determine, but whatever it's called, we can use the matter to energy conversion of elements to our advantage in our technology, and slowly migrate from a fossil fuel or hydrocarbon based economy where we burn huge amounts of carbon based energy storage media or elements, molecules, and release the energy within them to provide us with the energy for our technologies by using the deuterium nuclei as a storage of energy in the form of mass within its matter geometries. We can develop matter to energy converters and use them to charge up the deuterium nuclei and replace all our internal combustion engines, for example, with electric motors, where the energy is stored as mass alongside the electric motor and converted directly on demand to the wheels. This can be scaled up to any amount, so we can use it even for large haulage vehicles. Tetryonics gives us the technology to not only create the clean limitless energy from matter to energy conversion, but also store that energy in convenient matter geometries or large scale matter geometries, and distribute it for use on demand in a number of various ways within our current technologies. This is just the first step in utilizing matter to energy conversion, and in fact in future lectures coming up you'll see how we advance from these basic principles to a very advanced use of matter to energy conversions. Obviously Tetryonics gives us the key to doing this, and it was Tesla himself 100 years ago who said, and I quote, "To create and annihilate material substances, causing them to aggregate in forms according to his desire, would be the supreme manifestation of the power of man's mind, his most complete triumph over the physical world." What Tesla was saying here is, once we understand what creates matter and its distinction between mass and energy, and we learn how to harness the conversion of one form of energy from mass to matter and back the other way from mass into matter, we will have gained a huge step in understanding physics at every level, unifying the discrete fields of quantum mechanics, electrodynamics, chemistry and cosmology into a single unified understanding of energy in all its states and the role that energy plays throughout our universe. Tetryonics takes us on that step. We've covered fission in this lecture, and I thank you for your time. I look forward to discussing other forms of matter to energy conversion in future lectures.